Siri, turn the heater off. Oh, that's so much better. Okay. So we are done with this for the time being. Hit done. Let me check on you guys one more time. You look good. We are being live stream. Let me share my screen. Start the broadcast. Come on. And not too bad. Oh, let me get this to that. You got him, coach. All right, we're looking good. Okay, so let me start here. All right, so greetings, scholars. Let me see. So we are wrapping up chapter 2, it looks like, this week. So our goal for this week, we have 2 sections, all right? So no more 2-a-days. Well, not for right now. We're really going to focus on one section for today and then one section on Wednesday. So for today, we're going to focus on section 2.5. So that means exam 1 should be approaching, right? I think we have 2 exams. So I think that first exam is over chapters 1 and 2. I did a grade update, so you should be able to see your grades in Blackboard. Just check them for accuracy. If anything looks out of order, just bring it to my attention so I can we can resolve the matter. And so, I mean, at this point, you guys should be aware that, like, these intermediate grades throughout the semester don't really have any weight. They don't really mean anything. It's just feedback so you guys can have a sense of what I see. So we can kind of be on the same page, right? You don't want to be doing assignments and then they're not showing up. Either we're doing the wrong stuff and stuff like that. So, these intermediate grades are just feedback to inspect what we expect, right? Kind of thing. As usual, if you have questions about your grades, save it to the end of class. But if you have questions other than things about your grades, then feel free to unmute yourself to get my attention and we can talk about it or type it in the chat. Hope everyone had a great weekend. And yeah, so you might see my screen dimming. I got it in low power mode, trying to charge it. It was like on super low power. And, I just didn't charge it before class. So anywho. And this is, I kind of want to just like, I just want to say this next part is like it's like current event. So I've been seeing like demonstrations where people have been like showcasing the Apple Vision Pro. I feel like that's the beginning of the end. I don't know if you all have seen because I'm totally like, if I could get my hands on one, I would totally like just get one. But like I've seen videos of people like walking around New York with them on, and I guess like that's the vision I always saw when they came out with VR goggles. I was like, well, if you can do VR goggles, what's stopping you from doing AR goggles? So then Apple is the first to do an official AR goggle as far as I know. But if you've seen like the show Black Mirror, man, that's how it starts, right? It starts with this big goggle, then the technology gets smaller and smaller and smaller. Next thing you know, it's going to be, chips that, like Neuralink and stuff like that. They're putting chips in people's brains. So it has the same effect. But if you haven't seen that series, Black Mirror, you definitely want to check it out. Because they kind of touch on all this and show some like really zany but relevant like scenarios that can come out of this like near future technology. So I'm geeked about it. I mean, I am a tech head, but some of the pitfalls I see are like possible radiation, because even these phones cause radiation, and then like there has been an uptick in like people going blind, and I think it's just from like the blue lights from like the screens that we're always looking at and things of that nature. So I mean, it's exciting, but then obviously because it's new, it's gonna have like it's not gonna be fine tuned, so you have to kind of be careful. But it looks pretty cool. I saw another demo where so it's an augmented reality goggle where it overlays the virtual reality onto this reality. So it's like having a VR goggle, but you can actually see your surroundings. I was this close to getting an Oculus, and then when they came out with this, I mean, obviously the price tag is ridiculous, but that's how they always do when they first come out with this stuff. But I mean, it looks. I ain't gonna lie. I mean, it's like I get, I'm geeked. Like the one I saw with this guy, he was sitting at his desk. I guess he had some kind of keyboard or whatever, but he had the goggles on. And so because you can see your environment, I don't know if you ever play with AR, augmented reality or not, but it's fun. It's like you can put things in the virtual reality that stay fixed and you can move around, but it'll stay fixed in that virtual reality. So as you scan the room, whatever you put in the 3D space stays there. I've seen people like just do all sorts of things. It has so many applications. Like I'm telling you, I'm geeked about it because you can see so many different things. Like imagine we're still remote, but we're using the Apple Pro Vision to hold a math class. So I can have like my avatar at a digital chalkboard, and we can actually finally go back and forth, right? And it's not just me doing all the talking. The only reason I know this stuff is because I talk about it day in and day out. My task is to do my best to get you all to start talking about it. So whoever talks about this the most, learns the most, right? And honestly, that's kind of how life is. Like whatever we can focus on, whatever you focus your mind or your mental gaze upon the longest, that's what grows, right? So if we're constantly distracted, we have no power. Our power is very scattered. That's why we are inundated with like chasing money, social media, all these things. They don't want us to take the time to like go within, right? So, and this Apple Vision Pro is just another huge distraction, but it's all in how you spin it. You could spin it to grow, right? So anyway, I just had to like get a little rant. Let me see the time. So we got a solid 3 minutes before my second wave. Yeah. So, and there's more I want to say, but I don't want to eat up more of you guys' time talking about that. Let me see. So yeah, so we're wrapping up chapter 2 this week. Again, you can anticipate exam 1 to become available shortly. I can't think of anything else. So let's take some time to continue chapter 3 with section 2.5. So applications, exponential decay. A few objectives here. We like to find a function that satisfies dp by dt equals negative kp, convert between decay rate and half-life, and solve applied problems involving exponential decay. So with chapter 2, let me see. What have we been doing? I guess, let me see something. Exponential and log functions. So we've been applying concepts of the derivative to exponentials and logs, right? Okay, so let's keep going. All right. So let's see if the equation dp by dt equals negative kp, where k is positive, shows p to be decreasing as a function of time, and is a solution to, and the solution p of t equals p naught e of negative kt shows it to be decreasing exponentially. This is exponential decay, and the amount present initially at time equals 0 is p naught. So I think last time we worked a few examples where we were looking for some function p that would satisfy this derivative, right? So we were looking for some function p such that when we took the derivative of p with respect to t, we would get the result negative k times the original function, right? And so a function that satisfied that property was this exponential function. It's just in this case, we're looking at exponential decay, right? But it's similar to something that we talked about last time, okay? Let me see. So when we have exponential growth, our k is positive, right? So we have p naught e to the kt. And that's what exponential growth is going to look like, the image on the left. Then the image on the right, when k is positive, now we have p e to the negative kt. That's exponential decay. So it's like we flipped horizontally over the y-axis, like in college algebra 1, when we do transformations. When we multiply the inside of our base function by a negative, it flips it horizontally over the y-axis. So that's what happened here. It's like we multiplied the inside of our base function and flipped it horizontally. Okay, so that's on the right, we have that as exponential decay. All right. Let me see. So theorem 10, the decay rate k and the half-life t are related by kt equals a natural log of 2. We'll derive that at some point. The one that I tend to remember is, I think the last one, where t is your half-life equals the natural log of 2 over k, right? And we can derive it just for the sake of time. I'm just gonna forward on. Let me see the time. Can I see a clock? We still got like 45 seconds, maybe like 35 seconds, something like that. Anywho, okay, listen. So plutonium-239, a common product of a functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about negative 0.0028% per year. What is its half-life? So on the previous slide, we have what? Half-life equals the natural log of 2 over k. And it looks like they gave us the decay rate, right? Okay. So I think if we just apply the formula from the previous slide, I think we just jump straight to it. So and I'm gonna word it a little bit differently. Let me see. So the half-life should be the natural log of 2 over decay, which is your rate, your decay rate. So then they probably label it as T, which is the half-life. It should be the natural log of 2, the rate that's as a percent. So if we want that as a decimal, we divide by 100. So it looks like it's 4 zeros and then 28. Okay. And then we can just use the calculator for that part. I'm just going to say use the calculator. Just use my prepared notes. As long as we get this correct, then I think you can take it from there. So we see it here, natural log of 2, 1, 2, 3, 4 zeros, 28. Use your calculator if you get. So if you have like plutonium-239, if you have like a mound of it, it'll take almost 25,000 years for half of it. After 25,000 years, half of it decays, right? Half of it's going to remain. It's still going to be active, but only half of it's going to remain. So it has a 25,000 year decay rate. So that's probably why they use it in like nuclear reactions or whatever. Okay. So the radioactive, let me check on you guys in Zoom because I know we're at that time. Looks like we got a couple. Let's see. Got him, coach. Check. Yeah. Wait a minute. Oh, we must have lost somebody. I ain't gonna make a big deal about it. Not right now. Let's keep on moving. Give me just a moment. Oh no. Okay. It's close. I like to leave the blinds open during the day, but I don't like the blinds open to be open at night. It's just pitch black. You can't see anything out there. So, and I don't like people to be in there and see me like that at night. So, okay. So, example 2. The radioactive element carbon-14 has a half-life of 5730 years. The percentage of carbon-14 present in the remains of plants and animals can be used to determine age. Archaeologists found that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14. How old was the linen wrapping? Okay, let's give this a go. I do need some space. Let's see if I got a blank page somewhere. This is slide 9. Let's copy. Right here, I like to paste. No, come on. I know you were copied. Come on. Let me try one more time. Copy. And it even says it was on the clipboard. There it is, paste. Okay. All right, let me see. Oh, did I paste it in the wrong? All right, so let's kind of see what information they gave us. Now they gave us that the half-life is 5730 years. Okay. So it lost 22.3%. Okay, so I think this is all the information they gave us. And then they're asking us to find the age of the wrapping. So cut, paste. Okay, so a couple of formulas that might be in play here. Half-life formula, all right? The half-life equals the natural log of 2 over k, okay? And then it looks like we're working with exponential decay. So we can do like P of T equals P naught times E to the negative KT. Okay. So I think these are the formulas at play. So we're trying to solve for T from the exponential decay formula. Let's see, what do we have? It says it lost 22%. So if it started with P naught and it lost 22.3%, so let me see. That means the final amount, whatever it starts with, right? But we don't have that yet. I'll put it over here. So the final amount, P of T, is going to be, what is that? What's that difference? That would be 80, 78, 77.7. Right? So the final amount is going to have 77.7% of the original amount remaining, right? Okay. So if we tried to plug everything in, we got an expression for P of T. When we go to do a calculation, it looks like the P naughts are going to cancel. If we're trying to solve for T, we need something for the rate. So we can use that half-life formula to find our rate, right? So let me see, it gave us the half-life. So then that means the rate is going to be the natural log of 2 over 5730. Okay. All right, so that's the exact result. Okay, so let's see. Move it to the left twice. So if we put all this together, we have 0.777 P naught equals, I'll basically replace P of T with that, equals naught times E to the negative, or K, so natural log of 2 over this 5730. Let me make that look more like a 30 times T, right? So at this point, well, okay, we can divide both sides by P naught, and we'll have this 777 E to the negative natural log of 2 over the 5730 times T. So at this point, we have one equation, one unknown, so we can solve. If we want to get that out of the power, we take the, what on both sides? Take the, hopefully you're thinking, take the natural log on both sides. So what I'm going to do, I'm going to keep it exact until I get to the very end. The natural log is going to cancel out the E, and this allows us to bring this out of the power. So then at this point, we have negative natural log of 2 over the 5730 times T equals the natural log of the 777. So then ultimately, and I'll kind of work over here, the age should be equal to negative, let me see, if you flip and multiply, so it should be a negative natural log of the 777s. I'm just going to write it like this because I'm running out of space. Divided by the natural log of 2 over 5730. I think that's the exact result. And then we use our calculator to crunch that number. Let me see if I can get this number to work. This one. Okay, let's reload and refresh. And again, with an example like this, just try to pick up on the main points, right? Trying to follow every little step I do. Like one of the main points is in blue where we took the natural log on both sides. So like if you can get like these formulas, the starting formulas and the given details, and then try it yourself. If you get stuck, then refer back to what I'm doing. But try to take it as far as you can with that information using the formulas. And I'm hoping to have these done properly. Hopefully I haven't made a mistake. So let me finish it just to make sure. So we have, because I might have an error with my sign. Natural log of 0.777, come on. Divided by, I'm going to do the natural log of 2 over 5730. No, notice my use of parentheses. I think we're okay. How old is it? We would anticipate thousands of years old. So about, if we round up, 2086 years old, according to this. T is approximately, we said 2086 years old. Okay. So when I did it, I got this result. Let me kind of look at the prepared notes. Okay, so these are half-life to get the rate. And so then the rate is going to be the natural log of 2 over the half-life. Okay. So now they crunched their number, but notice when you crunch that number early, write out the long decimal. If you truncate that, it's going to throw out the final answer. So then this is essentially the same formula that we use, just different labels, but it's the same formula. And I think we started here. I think we had this, right? 777 of the original equals the original. I think we got this line, 2086. So the linear wrapping from the Dead Sea Scrolls is about 2086 years old. That's exactly what we got. Okay. I feel like there should be some questions. You know, I'm here. You just got to try. Like either, again, I don't really know aside from you all collaborating or making use of my office hours or connecting with the tutor. Also, Pearson, like on Pearson with the homework, every homework question has this like viewing example. It gives an explanation. You just have to like have a little bit of confidence and try. With a question like this, I would encourage you to, at least if you're like just practicing, start with the proper formulas and the given information. Plug in what's given and then just try it yourself. Don't like I know a lot of times like students get discouraged or discouraged, or what's the word I'm thinking of? Not imitated. I can't get it off for whatever reason. Intimidated is the word I'm thinking of, by these weird numbers, right? But you actually know how to work these, right? We're not really doing anything that much different than what we did before. But just kind of let those weird numbers be whatever they are. And then just see, for when I did, I kept mine exact until the end. The textbook, what they did, come on. They found this number, but they wrote out the long digit, and then you can see the work here, right, on how they did it. So we have two presentations to get us to the same conclusion. Pick and choose what you like from the presentations, whatever you resonate with, and kind of go from there. But yeah, okay, let's move forward. Okay, so that's a quick check. Let's try this example. Let me check on Zoom real quick. We already did our second wave, but I feel like we definitely got some. Okay. Hold on. Let me get these gentlemen. Let's see here. No, that's fine. Okay. All right. So let's try this example. Following the birth of their granddaughter, two grandparents want to make an initial investment of P0 that will grow to $10,000 by the child's 20th birthday. Interest is compounded continuously at 4%. That's a decent rate. What should the initial investment be? Okay. I need a page again. So let me get a copy of the other one that I used. Matter of fact, I should just be able to paste 15. Come on. My device is like, and it's because it's plugged in. But I can't unplug it. So this is actually size 16. Okay, let's paste it here. No, darn it. Okay, so size 16. Come on. Let's copy. And paste. Okay, and let's clear. Nice. Okay. All right. So they want to know how much they deposited in an account. They want the future amount to be 10,000 at a rate of 4%, and it's compounded continuously. Okay. So let's plug in what we have. So we're using exponential growth. P of t equals P0 times e to the kt, because we know exponential growth, so we did a positive exponent there. So we want the future amount to be $10,000. I think it said that the rate was 4%. It's compounded continuously. we're trying to solve for P naught. Was it 20 years? What was the time? This was at the time. On her 20th birthday, right? So 20 years. There is an owl outside just like having a real hoot. No pun intended. Well, actually, there was no pun intended, but no. But no, for real. He's out there just like going crazy. Not really that crazy, but he's just noticeable. The time was 20 years. Okay. Looks like I think we have all the information. Let's plug this information in. So we're trying to decide or find how much you need to start with. We said the rate is 4%. So as a decimal, that's going to be 0.04. And the time is 20 years. And we want her to finish when she reaches 20, she'll have $10,000. That seems like a long time for that amount. But the thing that's so beautiful about compound interest is that it just sits there and keeps growing. I'm going to tell the story after this example if I remember and I feel like we have time. I think we do have time. Okay, so that e to that power is just some number. So then ultimately, the starting amount is just going to be 10,000 divided by whatever that number is. E to the power of 0.04 times 20, right? And then from there, we use our calculator. I recently just got into like a new, I don't know if it's a hobby, but a new thing that I've never done before. And it's creating like juices, like tonic, like healthy juices or whatever. I came across some video of this guy. He gave some recipe for this juice. And he showed me how to like make the juice using tools that I already had. I always thought I needed like a juicer. He was like, no, you just need like a sieve. You need a strainer. So, we put the ingredients in the blender, blended it up, and then you just, sift it through the strainer. And now you got the juice. I was like, I don't need a juicer. I already have a juicer. Didn't even know it all this time. Okay. So now I'm making juices. It's fun. At some point, I plan to get like an ice cream maker too, like making like sherbets and things like that. Because like I feel like when I make my stuff, at least I'm aware of what's going in it. If I just buy it already made, I'm not aware of like how much sugar is going in it or like what type of sugar, But when I make it myself, I feel like awareness is, a lot of the issue. So we got our 10,000 divided by E to the power of 0.04 times 20. Okay, close off the exponent and close off the denominator. So it looks like they need to start with about 44.93 and 29 cents. 44.93, 29 cents. It looks like they need to start with $4,493.29. That's reasonable. That makes sense. Okay. So the grandparents needs to deposit $44.93.29, which will grow to $10,000 by the child's 20th birthday. Okay, so let me tell the story, and I'll put the story here. I'll do it in purple, I guess. So I don't know if I've shared this with you all or not, but I'm gonna share it now anyway. When I was a student at Morehouse, I was part of an honor society, and we were having a meeting or whatever, and they did this presentation, and the name of the presentation was called the Infinite Scholarship. Right? The Infinite Scholarship. And so what it is that they had an interest-bearing account that had 5% interest per year, and they were doing a fundraiser to raise $1 million. Right. So I'm like, an infinite scholarship. How do you have money that goes on forever? How do you have an infinite scholarship, right? So let's just count, and we're going to use the lowest form of interest. Now, if with better accounts or higher compoundings, we would generate more money. But the following is going to be the lowest money generated, right? So let's just look at the interest earned on this account. We're going to use simple interest, which is I equals PRT. Okay. So the principal is $1 million. The rate 0.05, and we just want to see how much is going to be in account after 1 year, right? So 1,000,000 times 0.05, we move the decimal to the right, what, 6 times? 1, 2, 1, 2, 3, 4, 5, 6, right? So with an interest-bearing account earning 5%, and if we deposit $1 million into that account and just let it sit, at the end of the year, we'll have $50,000. Right? That's pretty much a full-time check. That comes to about $3,000 or $4,000 a month, right? Do you think you can, like, just for letting an account sit? You think you can live off of maybe $3,000 or $4,000 a month? I know that's not like you're not balling, but that means you don't have to punch a clock. You don't have to be on a schedule. You can be essentially wherever you want to be. You know, I know people that have had that kind of money and that have donated it. And if it would have been a little bit wiser to create something like this, an infinite scholarship. People do GoFundMe's. People have money like this thrown around. I was watching this presentation this weekend that was talking about. I'll try to sum it up and be terse or concise or whatever, but it was talking about like people of color, and it was like we have the dollars, we just don't have the cents. Like we support, like we'll get our check and then we'll turn around, like I was talking about the Apple Pro. That's me trying to get my money out to somebody, some people other than us. Where other cultures, like they'll circulate their money amongst themselves 8 times before it leaves them, their group or whatever. And like everybody's making money off of us except us, right? And so he was just trying to encourage us to be more savvy and support, go out of your way to support Black-owned businesses and things of that nature. And I get it. I get what he's saying. I don't really know what it would take. Now, he one thing that he said was interesting in that presentation. He was like, before, like when everything was so segregated, we had our own businesses because we had to. Like if we couldn't use their stuff, then we would make our own stuff. We had our own taxi cabs and banks and laundromats and restaurants. We had everything, all right? Because we weren't allowed to, like, go out into society like that. So we just did it ourselves. And then, how they like to sabotage our efforts. And then, but after desegregation or whatever, since we didn't have to use our stuff, we didn't. And so all the businesses failed. Right. But I just thought it was interesting. I was like, I don't want to go back to segregation, but I'm just thinking like, okay, what does it take? What does it take for us to, like, get up out of this victimhood that we're like experiencing? Anywho, so what this is saying is that, as long as you don't go above like 3 or 4, whatever 50,000 divided by 12 is, like if you divide it by 10, that's 5,000, right? So as long as you don't go above about like $4,000 a month, you'll have money forever. As long as that account is open, you have about $3,000 to $4,000 every month. You can just do whatever with, right? Just for that account being there. Now there are some ways that we can like emulate this, even if we don't have this kind of money. And there are these things called like dividend stocks, where these companies will, give money back every certain amount of pay period, or whatever their timing is. But just for having stock with them, they'll give you something proportional to whatever amount you have invested with them. They'll give you money back. And I've met people that claim that they make a living just on the dividends they have so much money invested into these dividend stocks. It might not be as much as this, but it's enough to where they can just live off the returns from the dividend. So it's a little bit more aggressive, but it's also more risky than this technique, right? So trading in stocks and things of that nature. Just an interesting little story. So that's the infinite scholarship. Okay. Watching the clock. We're doing pretty good on time. I think we're okay. Let me check on you guys' Zoom, because I know we have people that like to trickle. Oh, okay. He must be on a couple of devices. I think he was doing that. We lost. That name looks familiar. Probably came in and left. Let me check. Where is he? I see that one. Oh no, he wasn't here. Okay, that wasn't him. Okay, but we got him now. Okay, let's keep going. All right, so we're actually almost done with this section. And I think we got all you. And then the present value of an amount P due T years later at an interest rate K compounded continuously is given by this. Present value. All right, so this is an application of the compound interest formula or the exponential formula, right? Because if we have P equals P not e to the KT, I just want to show you where this comes from, right? So in the previous slide, we had P equals P not e to the KT. If we wanted to solve for P naught, we would divide both sides by the e to the KT. But dividing by the e is the same as multiplying both sides by e to the negative KT. So then ultimately we'll get P naught equals P times e to the negative KT, right? It's still like the exponential growth formula. They just started on that first line and divided both sides by e to the KT to generate this formula. It's the same formula. Okay. I'm going to get rid of this. Okay. If you're joining us late, I did update grades, right? So your grades are there. You definitely want to check them for accuracy, make sure everything is in order. If you know you did something and it's not showing properly. Now, I think I did grades for you all. I think it was like yesterday. So, so just check them. If you submitted something past yesterday, then it'll just get in the next update. But again, just check your grades for accuracy to make sure things are in order. If anything is missing, just bring it to my attention and, we'll straighten it out. And the grades that you see now are it's just feedback. The only grade that matters is the one at the end of the semester. So this one that's here is just like, this is what I see on my end. Do you confirm or deny? Am I missing something? That kind of thing. The only one that matters, the only one that shows up in your transcript is the one at the end after the final. Okay, so we talked about this. What's the time? So then here we have another application on Newton's law of cooling. The temperature T, let me see. The temperature T of a cooling object drops at a rate that is proportional to the difference, T minus C, where C is the constant temperature of the surrounding medium. So the rate of change of the temperature with respect to time is given by this. The function that satisfies the above equation is T equal to A times E to the negative KT plus C, okay? Okay, this is fine. So that's Newton's law of cooling. Let's see it in action. So a body is found slumped over a desk in a study. A coroner arrives at noon, immediately takes the temperature of the body and finds it to be 94.6 degrees. She waits 1 hour, takes the temperature again, and finds the temperature to be 93.4 degrees. She also notes that the temperature of the room is 70 degrees. When was the murder committed? Ooh, I like this one. Let's see if we can get it. We need our page. So what slide is this? This is slide 22. Need a blank page. I think this one, let's copy. Slide 22 is here. Let's paste. And clear. Okay. Let me think. Give me a moment. The temperature of a cooling object. Okay. We have the temperature of the room. She also knows the temperature. So we have two of these. We're trying to solve for little t. Constant temperature of the surrounding medium. Let me see. Let's see, if we start here, we have two pieces of information. That's the rate of change. Let me take a screenshot. Do I need the screenshot? Let me take a screenshot of this. Come on. I really want that last one. That's the main one that I need. Come on. This is what I've been experiencing all day. Come on. And it just refuses to like register. What if I do? There we go. Oh, it's close. Okay. Almost there. Oh. That register is kind of, come on, there we go. I think part of the reason, okay, you know what? I'm not gonna use that. I don't know why my device is behaving like that. It probably just needs to be rebooted, which I don't have the time to do right now. But I think I can remember this. We're almost there. Like, there we go. Thank you. I just want to copy this. I'm gonna delete that. I'm gonna paste it here. I'm just gonna write it in. Man, my device is like, it's not responding. Okay, so we have this T of T equals A e to the negative KT plus C. That's fine. Oh, okay. Man, this is like, let me paste. Come on. I'm going to pull this other one as well. If I can get it to work. All right, I'm going to try unplugging it. I know it's kind of part of the reason it's throwing a tantrum is because I'm charging it and it just doesn't, it's not as responsive. I think with this one, d of t dt equals to negative k t minus c. I have an idea for this, but we'll check it out. Let me cut this. Okay, and let's paste. All right. So then let's also, they also gave us some information. They arrive at noon and the temperature is 94.6. So at noon, the temperature is 94.6 degrees. Okay. And then at 1 is 93.4. At 1 p.m., it's 93.4 degrees. So now the only one that I kind of want to start with the exponential decay function that they have, right? Or, okay, yeah, let's see. So we'll let noon be times 0, right? So the initial temperature, let me see, A e to the, so if the time, that's what we're going to let that be our time 0. So that temperature was 94.6 degrees, all right? Okay. So right now we have A plus C equals 94.6. Let me see. And then 1 hour later, so after 1 hour, let's see, let's just plug in what we have. We still don't have any specific information on A. The rate, I think we can get the rate from there, but I'm gonna come back to that. Let me see, so we got a negative K. We still don't know C, and that temperature is 93.4. Okay. Now it says the rate of change of the temperature with time is given by that negative K times T. Oh, and then the temperature of the room is 70 degrees. Okay. So it looks like from that rate above, we can find K, right? The rate of change of the temperature with respect to time. So then it looks like we can do something like 94.6 minus 93.4 over, well, that would be 0 minus 1, or, yeah. It's going to be a negative result there, which is, I guess, that's what's going to have to be. But then that's going to be equal to a negative, we don't know K, rate of change, T minus C. We have C. We're missing something there. Hang on. Let me see. We could get these both in terms of C. Okay. Okay. So I'm gonna backtrack a little bit because I'm not making a connection with this one. But from our given equations, we can set both of those equal to C, right? Let me give myself another center space, copy, or just duplicate and clear. All right. So from here, we can set the first equation. We can set both of these equations equal to C. So I kind of do that here. Right. So from the first one, well, I guess it might help us. Let's just go with it. So we get C equals 94.6 minus A. And then from the second one, we get that C equals 93.4 minus AE to the negative K. So then we can set those two equal to each other and just see what we can go from there. Just copy, paste. So then it should be the case 94.6 minus A equals 93.4 minus AE to the negative K. Let me see, can we just set this to 0? Okay. We just have one thing missing is the K. Oh, where did our time go? Right here, 93. Oh, that's after 1 hour, right? Mm-hmm. Let's see, the only thing we don't have is the rate. And I think we can get it from here, but I think I'm missing something from here. Rate of change of T. What if we take the derivative? That's gone. That persists times a negative K. Let me see. I'm going to kind of glance ahead, see what I'm missing. Okay, because what's our time? We're okay on time. Let me see. So we let T be the time elapsed in hours. Z represents noon. When they first took it, I think we got this. 94. The temperature of the room was 70. Did we forgot to include the 70, didn't we? Oh, we did forget that. That's 70. Let me see. So we can get A from there. Let me back up. All right. Before I do this, I think I'm making it a little bit more challenging. Right here. I forgot that the C is 70, right? So in each of these, they're equal to 70. So then if we add and subtract, so that means that A equals, what is that, 24.6? Okay. So then if that's our A, then in the second one, we have this 93.4 minus 24.6 E. So we're still trying to get to K, right? Equals 70. There we go. That's all we were missing. We forgot to plug in that the room temperature was 70, right? So then from here, we have one equation, one unknown. We can solve for K, okay? So then it looks like we have this negative 24.6 E to the negative K. What is that difference? It's going to be a negative 23.4. Okay. So then we divide E to the negative K equals 23.4 over 24.6. Take the natural log on both sides. So then the negative K equals the natural log of 23.4 over 24.6. So then ultimately K equals the negative natural log of this. Okay, so the only thing we were missing was this, the room temperature was 70. So then if this is our K, right, we're trying to find out when, I think we need another piece of information like the standard temperature of the human body. think it's like 96. Let me see. I think that's the other piece of information. A body is found slumped over this. Yeah, I think the temperature of the human body is generally like 96 degrees. I think we need that as well. I'm going to glance at the result. Yeah, we got all that. So now we have this. That's fine. Let me see. Determine the death. Here it is. A normal body temperature of 98.6 at the time of death. So that's like the general temperature of a human. That's what we needed. So I'm just going to use that. 98.6. Okay. Where'd it go? So then the temperature based on time, our A, we got 24.6. Come on. E to the negative KT. Come on. E to the negative K. I'm just going to put a star. I'm just going to, because I'm out of space. E to the negative K, and we're trying to solve for T. And then I think it's plus C. So plus 70. And then we want to use that the standard temperature of the human body is 98.6. So I'm going to do this. 24.6 e to the negative kt plus 70 equals 98.6. And then from that point, we have one equation, one unknown we can solve. Subtract 70. Okay. What is that? 28.6. Divide. Running out of space again. 20. That's fine. 28.6 divided by 24.6. Let me copy this. Because then we got to take the natural log on both sides. Copy. This one we want to duplicate. And clear. Paste. Nope. Undo. Copy. Paste. Okay. So then if we take the natural log on both sides, we get negative KT. Again, I'm just referencing instead of writing it out. Because, if we take the natural log, we get the natural log of 28.6 over 24.6. Actually, that's a T. And ultimately, the time is going to be the natural log of the 28.6 over 24.6 divided by a negative, whatever star is. The star is, so it's a double negative, so it's going to end up being positive of this guy. Copy, paste, and again, double negative makes it positive. Okay. So that's when it's going to be. Okay, so now we got to the bottom of it. It was a little bit choppy, but we got there. What's the time? And it's just about time for us to go. Let's see if we can get this number to work. 28.6 divided by 24.6. And then that log divided by 23.4 over 24.6. Okay. What are we missing? 28, 24, 23.4 over 24.6. Something seems off. I don't know if that's right. And we're kind of short on time. Let me see. Let me go back and look real quick. I feel good about this. We got our A to be 24.6, E to the negative K times T, 70, 98.6 was the temperature. Subtract 28.6, divide 28 divided by 24. Take the natural log. Mm-hmm. I feel like we might be missing a negative. Let me see. So we got this, we got that. The K was the negative of that. Mm-hmm. I think we got an extra negative in there. No, no, they did it. Let's keep going. Right here. 28 over 24. Yeah, we got that. Why is the number not working? 23 over 24. Mm-hmm. And we had a double negative there. I feel like we got a sign off somewhere because I think I remember something similar happening. But I can see it there, and it's there. Let me see if I right here. I think there's supposed to be a negative here. Let me insert. I think that's okay. No, that doesn't change. 28.6 over 24.6. Oh, okay, I found it. I was missing my log when I typed it in the calculator. I knew it was something in the calculator. Okay. Now they got a negative. Let me get rid of this. Let me insert. I didn't hit the log when I put in the calculator. That's what okay. Let me delete this. Let me see. I can delete that. And I think we're good. There we go. Yeah, I was just missing the natural log. So everything we did was fine. Our work was right. We just typed it in the calculator wrong, right? I think when I looked at it again, I forgot to hit the second set of natural log, but everything else is good. Praise the Lord, right? I thought that was an adventure, right? But we got to the bottom of it. Okay. So oh no, okay, we can plug you in since we passed all that now. So since t equals 0 represents noon, the time of death was about 3 hours early, right? So about 9 a.m. That's interesting. I kind of want to recap that and we'll call it a day. Um, so with that one, I didn't really use that other part. I kept trying to force myself to use it, but we didn't. I ended up not really using this. The main thing was this one. All right, we started here. The information we were given was at noon. It was 94, and then 1 hour later, it was this, and the room temperature was this. We did forget to include that at some point. So we let noon be the time at 0. All right, we plugged in whatever we had, and then the corresponding temperature was this. We also forgot to plug in the 70 there, right? So if we had plugged in 70 there, we would have generated this result quickly, right? So we forgot to plug that in. To the second equation, let me see, 1 hour later. So then you have we just found a wheel temperature of the body 1 hour later was 93.4. Okay. So then from there, the only thing we didn't know was K. So okay. Right. And instead of like crunching the number or constantly writing that over, I just made a reference. I just called it star. Right. So then we went back to that same formula, A e to the negative K T plus C. And then we plugged everything in. We had our K. We're trying to find T. We had everything else. All right. So then at that point, it was one equation. And again, the general temperature of the human body was 98.6. I knew I had to look that one up. I just didn't remember it. I was trying to do 96 something, right? So we plugged in the A we found, we plugged in the K we found, we plugged in the room temperature and the standard temperature of a human body. Only thing we didn't know was T. So then from there, it was just solving for T, 0.6, taking the natural log on both sides, and then the natural log of the right divided by K, divided by negative K, right? And so then we get T T was approximately negative 3.01 hours. All right, we got the same thing. And again, we made another mistake in the calculator. We forgot to hit that. Okay. So that one was a little intense, but we got to the bottom of it and it was fun. Okay. All right. Why did I say 29? Wait a minute. This thing is, why does it say 27? That's not right. Anyway. Okay, so we saw some applications of like half-life and things of that nature. And then Newton's law of cooling, right? So that was just an application. All right. Again, I feel like there should be questions, so you just have your work cut out for you. Again, so that's why I do like unlimited attempts on these assignments. The system is set to take your highest score. Again, with that 5% late penalty, the system wouldn't let me. I guess because we had already started. So whenever I went to change those, whatever we had already got accumulated grades for, it wouldn't let me change the late penalty. But from that point forward, the remaining assignments all had a late penalty of 5%. So some assignments have a late penalty of 10%. I changed as many of them as I could to a late penalty of 5%, right? So it's just work. It's just like you're just gonna have to push. Don't hesitate to make use of the Ask My Instructor. It'll send me a screenshot of your question. If you just stuck, I can walk you through it as best I can. And, are there any burning questions before we go our separate ways? So we have, I think, one more section in this chapter. Let me make a copy of this available to Box. It's not the right folder. Spring. Traditional calculus. Notes. Updated daily. This is week 5. I think this is correct, 2.5. Okay. So we did the best we could with section 2.5 today. And then on Thursday, we'll be working on section 2.6. And I think that'll bring us to the end of chapter 2. And we'll be ready for exam 1. All right. So if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day, gentlemen. And I'll see you Wednesday, same time, same place. Take care. Peace.
I see you.
Here. Let me check Zoom real quick before we get out of here. Come on. Let's see. I think we got participants. Let me check the chat. Oh, yeah, Mr. Davis, I got you. Yeah, I got this. No worries.